everyone! In this lesson, you will explore how the idea of sums of squares appears in topics that you already studied, specifically the distance formula, the equation of a circle, and the search for integer points on a coordinate plane. Even if you don't notice it at first, many familiar formulas in geometry and algebra secretly come from simple expressions involving squares, such as a squared plus b squared. By the end of this tutorial, you will understand where these formulas come from, how they are connected, and how you can apply them through actual examples. You begin by understanding what a sum of squares is. When you add two squared quantities, such as a squared plus b squared, you are dealing with the sum of squares. This expression appears naturally when you measure distances, when you study shapes, and even when you analyze points on a coordinate plane. The moment you learned the Pythagorean theorem in grade 8, you are already working with sum of squares. That idea builds the foundation for more advanced lessons in grade 9 and grade 10. And here it goes, the Pythagorean theorem, which states that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. In short, c squared is equal to a squared plus b squared. When you place a right triangle on the coordinate plane, the horizontal and vertical sides can be found by subtracting coordinates. If you have 2 points, x sub 1, y sub 1, and x sub 2, y sub 2, the horizontal distance is the inner product of x sub 2 minus x sub 1, and the vertical distance is the inner product of y sub 2 minus y sub 1. Using the Pythagorean theorem, d squared is equal to the quantity of x sub 2 minus x sub 1 squared plus the quantity of y sub 2 minus y sub 1 squared. Taking the square root gives the distance formula. So every time you find a distance between 2 points, you are using a sum of squares. Now you can apply the formula. For horizontal change, we have 8 minus 2 is equal to 6. 5 minus negative 1 is equal to 6. For the application of the formula, we have d is equal to square root of 6 squared plus 6 squared, which is equal to the square root of 36 plus 36, the square root of 72, and now for the simplification, we have the 6 square root of 2. You just use a sum of squares to calculate distance. A circle is a set of all points that have the same distance from one fixed point. You call this fixed point the center, and the constant distance is the radius. So if you imagine a point moving around but staying the same distance from the center, it traces a perfect circle. Now, suppose the center of a circle is located at HK and the radius has a length of r. To check whether a point xy is part of the circle, you measure how far that point is from the center. And the tool you use is something you already know, the distance formula, which itself came from Pythagorean theorem. The distance formula tells you that the distance between the point xy and the center hk is r is equal to the square root of the quantity of x minus h squared plus the quantity of y minus k squared. Now, notice something immediately. Inside the square root, you already see the same pattern you've been working on, the sum of two squares. To remove the square root and make the formula easier to work with, you square both sides. And this will be r squared minus the quantity of x minus h squared plus the quantity of y minus k squared. This equation is extremely important. It is the standard equation of a circle, and it tells you a point is on the circle if and only if the sum of these two squared distances from the center equals r squared. Every single circle in the coordinate plane is defined by this one equation, and you can clearly see at the heart of it. The entire formula is literally built from a sum of squares. For our next example, we have determine whether the point 4, 1 lies on the circle centered at 2, -1 with radius 3. To check if a point lies on a circle, you don't need to draw anything. You simply test whether the point satisfies the circle equation. The center is 2, -1, and the radius is 3, so you check. The quantity of 4 minus 2 squared plus the quantity of 1 minus -1 squared is equal to 3 squared. And to compute each part step by step, this will be 4 minus 2 is equal to 2 and 2 squared is equal to 4, while the other is 1 minus -1 is equal to 2 and 2 squared is equal to 4. So the left side becomes 4 plus 4 is equal to 8, and the right side is 3 squared, which is equal to 9. So the final comparison is 8 is not equal to 9, because the sums of squares on the left side do not equal the radius squared. The point does not lie on the circle. And this example shows that even when you are checking circle membership, you are still using the same idea. You square the differences and add the squares. Next, we have what are lattice points, a point in a coordinate system where both its coordinates are integers. You now move to the topic that connects geometry and number theory, which is the lattice points. These are simply points whose coordinates are both integers. For example, we have 0 and 3, -4 and 2, and 5 and 0. These points lie exactly on the grid intersections of the coordinate plane. Sometimes, you want to find which lattice points lie on a circle. To do this, you use a simplified form of the circle equation. If the circle is centered at the origin 0, 0, the equation becomes x squared plus y squared is equal to r squared. And here again, you see the pattern of a sum of squares. Finding lattice points on a circle now becomes a matter of asking, which integer pairs x and y have squares that add up to r squared? This means your geometry question becomes a number theory question. You search for a perfect square combination that produces a specific number. For our next example, we have find all integer points satisfying x squared plus y squared is equal to 25. So you want all integer pairs whose squared values add up to 25. So you list all the possible perfect squares less than or equal to 25. We have 1 squared is equal to 1, 2 squared is equal to 4, 3 squared is equal to 9, 4 squared is equal to 16, and 5 squared is equal to 25. Oh, and I forgot to put the 0. 0 squared is equal to 0. Now, next is you look for pairs that add up to 25. We have 0 squared plus 5 squared is equal to 25. So the corresponding integer points are 0, 5 and 0, -5. So you pair it up. So 5 squared plus 0 squared is equal to 25. So you also have the 5 and 0 and -5 and 0. Pair 3, we also have this 3 squared plus 4 squared, which is 3 squared is equal to 9 and 4 squared is equal to 16, so that is add up to 25. So this gives 4 more points because signs can vary. So we have 3, 4, 3 and -4, -3, 4, -3, -4. So for final answer, we have the 8 integer points. There are only lattice points on the circle of radius 5. This example beautifully shows how the simple structure x squared plus y squared connects geometry, algebra, and number theory all in one topic. In this final part of the lesson, you reflect on how a single mathematical idea appears again and again throughout your journey from grade 8 to grade 10. Even though the topics you study each year seem different, many of them are actually connected by one shared structure, the idea of adding two squared quantities together to measure something meaningful. You first encountered this idea in grade 8 when you learned about right triangles. At that point, adding two squared values allowed you to determine the longest side of a triangle. This was your first experience with using squares not just as numbers, but as tools that capture distances and measurements. You learned that the legs of a triangle, when squared and added, describe the exact length of the diagonal side. This idea became the foundation of many practical applications, such as knowing how high something reaches, how far something extends, or how steep something rises. When you moved to grade 9, this same concept appeared again, but in a new form. This time, instead of triangles drawn on paper, you work with the points on coordinate plane. You learned that to find the straight line distance between any 2 points, you rely on the same kind of thinking. You measure the horizontal change, you measure the vertical change, you square these values and combine them. Even though the problem now lives on the grid instead of inside a triangle, the structure behind it is exactly the same as the one you used in grade 8. What changed was the setting, but the mathematical idea never disappeared. Then in grade 10, the idea continues to grow. Now you apply it to one of the most important shapes in geometry, the circle, as you define it as all points that remain the same distance from a fixed center. And then, to express this distance on the coordinate plane, you once again rely on the same technique you already mastered, comparing horizontal and vertical displacement, squaring them, and combining them. What looks like a new formula for a circle is actually nothing more than the distance concept written in a new way. This means that the circle equation is not a new topic at all. It is simply the old grade 8 idea expressed at a higher level. Beyond these lessons, you also learned about special points called lattice points, points whose coordinates are whole numbers. When you search for lattice points on a circle, you are actually solving a number puzzle. You look for squared values that fit together perfectly. This turns geometry into a form of number exploration. You discover that certain whole number pairs naturally form circular patterns and others do not. Once again, the same structure appears, but this time it connects geometry and number theory. When you step back and look at the bigger picture, you realize something important. Your math lessons are not separate islands. They are parts of one larger interconnected system. When you learn in one grade level prepares you for the next, the idea you study about right and triangles in grade 8 develops into distance concept in grade 9, then grows into circle equations in grade 10, and throughout these transformations, the same pattern, the combination of two squared measurements, remains the center of everything. This is the real beauty of secondary mathematics. The deeper you look, the more you realize that many lessons share the same heartbeat.